We have estimated enthalpy changes for reactions using Hess's law and using heats of formation. We can also use individual bond energies. So the bond energy is the energy needed to break 1 mole of those bonds in the gas phase. Bond energies are always positive. It always requires energy to break bonds. They don't break spontaneously. A bond is stronger if it takes more energy to break. It kind of makes sense. So here we have HCl, that bond breaking to form a hydrogen atom and a chlorine atom, and delta H for that is 431 kilojoules. That is the energy required to break that bond. Compounds that have stronger bonds tend to be more stable. They tend to be less reactive. Makes sense. Their bonds are strong, right? Things aren't going to just fall off. So bond energy is going to vary depending on the exact situation. So here we can look at a carbon-hydrogen bond in methane. So the other things are hydrogen. Here the other things are fluorine, bromine, chlorine. These are all carbon-hydrogen single bonds. The energy required to break it is different depending on the compound. So what we look at in a table is average bond energies. And as you might suspect, double bonds and triple bonds have higher bond energies. So this is a table of average bond energies. And so you can go in here and see, I have a carbon-nitrogen double bond. Okay, that's going to take this much energy to break. One thing I'd like to point out here is carbon-oxygen double bond is 736 on average, unless you're talking about CO2, and then it's 799. So the way we can use this is by looking at what bonds have to be broken and what bonds are formed. So breaking bonds is endothermic. You have to put energy in. Forming bonds is exothermic. So the bond energy is the energy for breaking the bond. When a bond forms, you get the negative bond energy. So basically, we're adding up all the energies for the bonds that get broken and formed, and that will give us an estimate of the enthalpy of reaction. So again, we can talk about final see how they put a plus in there? They didn't do this on the other one. You can think of this as the bonds of the products actually you can't, never mind, scratch that. So here's the idea. If we've got methane and chlorine reacting to form these two guys, what bonds have to break? Well, this chlorine-chlorine bond has to break. So we figure out the energy for that, and this carbon-hydrogen bond has to break. So we find the energies to break those two bonds, and then what gets made? Well, we make a chlorine-carbon bond, and we make a hydrogen-chlorine bond. So we find out what those are. Those are going to be negative and lower in enthalpy, releasing energy. So we often say that energy is stored in chemical bonds, which kind of is wrong. Breaking a bond always requires energy. It's the forming of chemical bonds that releases energy. So the energy is coming from the formation of bonds. So it's related to chemical bonds, but it's not that it's stored in the bonds, it's from the creation of the bond. So energy-rich compounds undergo reactions in which weak bonds are broken and strong bonds are formed. The reaction between hydrogen and oxygen to form water is highly exothermic. Which statement is true of the energies of the bonds that break and form during the reaction? So energy needed to break bonds is greater than the energy released. The energy needed to break the bonds is less than the energy released, or they are about the same. Break is less, right? This is highly exothermic. A lot of energy is going out, which means the bonds that are being formed are stronger than the bonds that are being broken. So the energy required to break the bonds is less. So a potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So I'm not going to really do this whole problem because it's really tedious and I don't think it's super important. But let's kind of outline it. So we need a chemical reaction for the combustion of CH3OH. What is the other reactant? O2. And what products are going to form? CO2 and H2O. Because that's what you get when you burn organic compounds. Lost my O. Okay, so then we need to balance this. Right? So 1 carbon and 1 carbon. And here we've got 3 oxygens and 3 oxygens, 2 hydrogens and 4 hydrogens. So if I put a 2 over here, now my hydrogens are balanced, but my oxygens are messed up. So now I've got 2 oxygens and 2 oxygens, and then over here I have 2 plus 1 is 3. If I put a coefficient on the methanol, that's going to mess up everything. So this is where I need to get an odd number of oxygens out of this, and that's what I call the odd-even problem. So I'm going to double everything so that we get rid of the odd. So I'm going to put a 2 here and a 2 here, and I'm going to change this 2 to a 4. I didn't put anything here because this is the one I'm trying to figure out. Now I have 2 carbons and 4 times 2, 8 hydrogens, 8 hydrogens. So over here I have 4 oxygens plus 4 oxygens is 8 oxygens. And over here, this is 2 oxygens. So I need there to be 6 from this. So I need to put a 3 there. So you could calculate this by just looking at which particular bonds need to be broken and which are going to be formed. In my mind, that requires a lot of thinking, and sometimes it's better to just do the long way that's easier. So the long way that's easier is saying, let's break all the bonds and remake all the bonds. And to do this, we have to look at the Lewis structures, because we need to know what kind of bonds we have. As I said, this is tedious. So those are the sorts of bonds that are here. So we can look up the total number of bonds that are being broken. So to break this thing up, I'm going to have carbon-hydrogen bonds that get broken, right? There's 1, 2, 3 for this one, and there's 2. So that's 6 of those. And the oxygen here, this is an oxygen, double bond. Oh wait, let's not go there just yet. So we pulled those hydrogens off. We can pull the hydrogen off the oxygen, so that's an oxygen-hydrogen bond. There's 1 in this compound, there's 2 of them, so 2, and then pulling apart the carbon-oxygen. 1 of those bonds in the compound, 2 of the compounds, there we go. And then here we have oxygen, double bond. 3 of these molecules, so 3 of those bonds. So then you go and you look up the bond energies. Come on. So carbon-hydrogen bond, 414. So 414 kilojoules per mole. And there's 6 of them, so it's 6 times that. There's 2 of these, so 2 times the bond energy for that one. 2 times the bond energy for this one, 3 times the bond energy for that one. You add those all up. Those are breaking the bonds. This is going to be positive. Then you look over here and you see, well, what kinds of bonds do I have? Well, I have this carbon-oxygen double bond. I have 2 of those in 1 molecule. I have 2 molecules, so there's 4 of these. And if we look it up, this is that exception, and this is the 799 kilojoules per mole. And then making. So I'm making these, and I'm making these. I got it backwards. So here I have to make 2 oxygen-hydrogen bonds, 2 for this 1 molecule, but I have 4 of those, so that's 8. So then 8 times this. And I'm going to add those up. And this is going to be negative, because this energy is released. So I've got this amount of energy being released and this amount of energy being used. I add those 2 numbers together, and that's my estimate for delta H for the reaction. Does that make sense? There could be a question on an exam, but it would not be anything as complicated as that. It would be something simple. Bond lengths. Again, we typically look at averages for these because the actual length of bonds can vary from compound to compound. But double bonds are going to be shorter than single bonds, and triple bonds are shorter than double bonds. So the triple bond is going to be the shortest and the strongest. The double bond is in the middle, and the single bond is the longest and the weakest. So those are average bond lengths.